Hi, am I audible? I am talking right now. I am not sure if you're able to hear. Okay.
Am I audible?
Yeah, you are.
Yeah, fine. We'll start off then. So, hi guys, it's me Daniel, and I'm going to take a session on optimizers today. We'll start off then. Okay, before diving into optimizers, we'll look into several other things which form as the basic for that. So, the first one is going to be neural networks. So, neural networks are one among the many machine learning models which I used to train a particular data set. So we'll be covering the very basics of neural networks today because you guys will be learning in depth about these neural networks in the upcoming sessions. So as the name suggests, neural networks are inspired from the functioning of a human brain, and they are designed to recognize patterns and perform tasks such as classification, regression, and data processing. So a typical neural network looks something like this with multiple layers, and each layer is going to be made up of several number of nodes, and these nodes are going to be termed as neurons. So as you can see, we have an input layer over here which consists of three neurons, and they are going to be color coded with the blue color. So the role of this input layer is that uh, whenever we receive or whenever the model receives an input data, the features which form the data set is going to be distributed among these neurons, and this will be passed on to the next layers which are called as the hidden layers. They are going to process on this data, and they'll be providing the output to the final layer which is the output layer, and output layer further process the data and gives us with the final output. So this is basically how a neural network works, and again, as I mentioned earlier, you'll learn in depth about neural networks in the next session. So the next thing which we have to know before getting into optimizer is a loss function. So now we have a neural network over here. We are going to pass on an input data X. And once the model is done processing the data, we are going to receive a, you know, uh, we are going to receive a final output of Y prediction. And at the same time, we are also having an output Y, which is going to be the true output that corresponds to X. So what basically the loss function does over here is that it's going to mathematically define the deviation of this y prediction from the true output y. So that is basically what a loss function does. There are several different types of loss functions, and the one of the most used and one of the most prominent ones are going to be the mean square error, which I have placed over here. So it's going to be given by the formula 1 by 2m times of summation of y hat minus y the whole square. Here, the y hat value is going to be of the true output y, and y is going to be the predicted output, and m is going to be the number of epochs. So this is it about our loss function. Now we'll get on to what is an optimizer. So optimizers are algorithms or methods used to minimize an error function or loss function, or to maximize the efficiency of the model. Now, optimizers can be thought of as the mathematical functions which depend upon the learnable parameters, which are weights and biases in our case, because we are going to use the neural networks in our case for this session. So, what basically optimizers do is that they're going to help us reduce the path or the certain alterations which we have to do to these learnable parameters, such that the loss function is going to be ultimately minimized, because the basic idea behind training our model is to reduce the error in our prediction model. So that is why we are training the model. So optimizers help us with that. So how exactly do they do it? So that's where loss function comes into picture. So we have been discussing about reducing the loss in our model and all that, but we'll try to put it in a graphical manner rather than just words. So we have a loss function. Now, when we have to reduce the error in the overall model, the main goal for us is to attain the global minimum of the loss function. So optimizers help us by traversing the model along the loss function so that we'll be able to land at the global minimum. The main point to be noted over here is that we need to land at the global minima and not the other local minimas, because we want the error to be as minimum as possible. So that's the idea over here. So this is going to be the graphical or the pictorial representation of whatever I've explained so far. So we can see over here, along the z-axis we have plotted the loss, and along the xy plane we have the two learnable parameters, which are theta naught and theta 1. So let's imagine it to be a piece of fabric, and we are holding it from four different corners, and now we are going to place a ball somewhere over here, and we are going to just leave it. So after a while, the oscillations will die out, and the ball will come to a rest. So that point where the ball comes to a rest is going to be called as the stable equilibrium point. And in our case, that is going to be the point where the loss is going to be minimum. So the basic idea behind optimizer is that we are going to figure out that point, and we are going to figure out the learnable parameters at that specific point. So now we'll move on with the types of optimizers. So basically there are five different families of optimizers. The first one is going to be the gradient descent family, which consists of batch gradient descent, stochastic gradient descent, and mini batch gradient descent. The second one is going to be accelerated gradient descent family, which consists of momentum based operators. The third one is going to be adaptive learning rate methods, which consists of several different optimizers like AdaGrad, RMSprop, and AdaDelta. We'll be looking into the details of RMSprop in our session. And the fourth family is going to be of Adam family operators, and we'll be looking into the details of Adam operator in this session. And the last one will be look ahead. Look ahead optimizers are not exactly an optimizers by themselves. They can be combined with the remaining specified operators to enhance their ability. So that's why they are called orthogonal to the remaining operators. So let's get on with gradient descent first of all. So gradient descent is one of the most basic and one of the most used optimization algorithm. So it's heavily used in linear regression and classification algorithms. So what is the basic idea behind gradient descent? So here in gradient descent, the movement is going to be in the direction of the steepest descent till the global minima is found. So what does it mean? So if you guys would have noticed the climbers climbing down a hill, they would always take the path which is the steepest. So why are we doing so? Let's take an example, or let's take the picture over here. So the steps which we are going to take can be thought of as the steps which we are taking along this direction, which is the x direction. So for the same step which we are taking over here, since the gradient is very steep over here, we are going to cover a lot of distance along y-axis over here. Whereas if the gradient is not very steep over here, for the same distance which we are covering in x-axis, we won't get that much of a coverage in the y-axis. So that is the reason in gradient descent, we are moving in the direction along which the the descent is steepest. So that is the basic idea behind gradient descent. Now, so as I mentioned earlier, we are going to take several quantified steps towards the global minima. So these steps are going to be quantified as learning rate. So what is learning rate? Learning rate is going to be the hyperparameter, which, as I mentioned earlier, is going to quantify these steps which we are taking along the direction of steepest descent. So now that we know learning rate is a hyperparameter, which also means that the user has to fine tune it. How do we fine tune it? That might be our next question. So before getting into how do we fine tune the hyperparameter, we have to know the consequences of setting the hyperparameter at two different extremities. So let's take the first case where our learning rate is too low. So when the learning rate is too low, it means that the span of the steps which we are taking towards the minima is going to be less. That means that the time which we are taking to attain the minima is also going to be very high, which ultimately leads to the decrease in efficiency of a model. So because of the increase in computation, our model's efficiency is going to come down in this case. And now let's consider the case where the learning rate is too high. So in this case, there is a very high chance that whenever we are closer to the minima, if the learning rate is high, there is a very high chance that we'll be overshooting the minima in the next step which we are taking. So that is the reason, setting the learning rate to a very high value is not plausible in most cases. And even at several times, there is a high chance that we'll be oscillating between two extremities above the mean. about the minima. So, so now that we know the consequences of setting the learning rate at two different extremities, what exactly should we set the learning rate to? So the learning rate should be somewhere in between these two extremities. As we are going to fine tune it anyways, the starting point of the learning rate can be somewhere in between 0.01 to 0.1. So that's about learning rate. Now that we know about all this stuff, let's move on with the updation of parameters. Because the main idea behind optimizers, as we have seen earlier, is going to be the changing of the learnable parameters so that the loss function is going to be brought down. So the updation of parameters in a gradient descent is going to be given by this formula, wherein x is going to be the parameter concerned and LR is going to be the learning rate, whereas dy dx of f of x, in that we know f of x is going to be the loss function, which basically means that this whole thing is going to be the gradient of the function at x. So this is the formula according to which we are going to update the parameters. Okay, I mentioned about the fine tuning of hyperparameters till now. I have a slider quiz over here for you guys. So basically, the idea over here is that we have four different, color coded lines which correspond to the quality of learning rate. Which is to say, we have four qualities. Very high learning rate, good learning rate, and low learning rate. So I want you guys to mix and match these four differently color coded lines to their respective quality of learning rates. So I'll give you guys 2 minutes to scan this code and answer. So okay, so I mean, almost half of you guys got it right, and the remaining half confused between the good learning rate and the high learning rate. Guys, what is it? Ah, okay. Fine. I'll explain it then. So yeah, as you guys can see, the yellow curve here is going to correspond to very high learning rate, and the green one is going to correspond to high learning rate, and the red one is going to be good learning rate, and the blue one is going to be low learning rate. So I think the yellow one was very obvious. Most of you guys confused between the green and red one. So I'll explain. So whenever the learning rate is high, it means that it will be able to traverse the loss function so fast that it will be able to come closer to the minima, in a very short time compared to that of a good learning rate model. But as I mentioned earlier, there is also a chance that the model will be oscillating in between two extremities whenever the learning rate is high. So this is one of those cases, as you guys can see. After a certain point, the loss started, stabilizing. So that is a consequence of this model oscillating about the minima. So whereas for the whereas for the red color coded curve, you can see even after this particular point, the model is still trying to reduce this loss. So that is basically why the red one corresponds to a good learning rate, whereas the green one corresponds to the high learning rate. So I hope you guys are clear with this. We'll proceed then. Okay. So now we'll discuss the types of gradient descent. So the first one is going to be stochastic gradient descent, which we'll be discussing over here. So what does this word stochastic means? So stochastic means a randomly defined process, and the same thing is going to be applied over here. So in a normal gradient descent, or also referred to as the vanilla gradient descent, we saw that we are going to calculate the gradient descent for every individual parameter. Now let's take an example. Let's say we have 10 parameters and we have to perform gradient descent for all those 10. So in a vanilla gradient descent, we'll be calculating the gradient descent for each and every one of those 10 different parameters, and we'll be updating each and every one of those parameters based on their corresponding gradient descent. Which is to say, let's say we have 10 parameters. Among that,
Daniel, did you move to the next slide?
Is it on stochastic gradient descent? No?
It's still on the Slido question. Can you stop sharing and share it again?
Okay, 1 second.
Are you sharing the entire screen or only the window?
Yeah, I'm sharing my entire screen now. Is it visible?
Yeah, the screen is visible. Just move through the slides once to see if it works.
Yeah, is it working?
Yeah, now it is.
Yeah, fine. Yeah, so I'll go through stochastic gradient descent once more again. So the word stochastic means a randomly defined process. And yeah, to understand it better, we'll take an example. Let's say we have 10 parameters. In a normal gradient descent or vanilla gradient descent, for all the 10 parameters, we'll be calculating their corresponding gradient descent, and we'll be updating the individual parameters based on their corresponding gradient descents. Whereas in stochastic gradient descent, what we're going to do is that since we are going to have 10 parameters, we'll choose one random parameter out of those 10 parameters. Let's say we are taking, the 7th parameter. We are going to calculate the gradient descent for that 7th parameter. And with that gradient descent, we are going to update the remaining parameters, which is to say from parameter 1 through 10. So I hope you guys got the difference between stochastic and normal gradient descent. If not, I'll try to explain it once. So in a normal or vanilla gradient descent, we'll take the first parameter, we'll calculate the gradient descent for that, and at the same time, we'll be updating the first parameter based on the gradient descent calculated for that. Whereas in SGD, we won't be using the corresponding gradient descents to update those parameters. We'll be taking one random point or one random parameter out of those entire set of 10 parameters, and we'll be using the gradient descent for that one
parameter to update the remaining parameters. So that's how stochastic gradient descent is different. So now, why are we doing this? What is the reason? So the main reason behind the stochastic gradient descent is that it reduces the computation time. So the whole process of calculating gradient descent for all the parameters and updating the parameters based on those individual gradient descent is going to be a hassle, and it ultimately increases the computation time and thereby reducing the efficiency of a model. So to prevent that, we are implementing SGD. So that is the idea behind SGD. Now let's move on to the next one, batch gradient descent. So batch gradient descent is going to be a bit different from vanilla gradient descent as well. Let me explain the difference again. So we'll take the same example again. So now we are going to have 10 parameters. What happens in batch gradient descent is that we are going to calculate the gradient descent for all the 10 parameters, just like we do for vanilla gradient descent. But here, instead of updating those parameters with the gradient descents calculated for the individual corresponding, for the corresponding parameter, we are going to take the average of all the calculated gradient descents, and we'll be updating the remaining parameters based on that one averaged out gradient descent instead of using the corresponding ones. So yeah, I hope you guys got the difference between batch gradient descent and normal gradient descent. So again, why are we using this over the normal gradient descent is that, over the SGD is that it's going to be a lot more accurate than SGD. It's typical because in SGD, we don't exactly mean to represent the whole data set with one single point. So let alone 10 points, let's say we have some 10,000s of parameters. Among that, we are going to just choose only one parameter to represent all the remaining parameters. That is not going to be very ideal because that will introduce a lot of random fluctuations into our data. So to prevent that, we are using batch gradient descent, because here since we are going to take the average of the gradient descents, it's kind of more representable than the SGD. So that is the one advantage of BGD over SGD. But the disadvantage of this over that is obviously going to be the computation time. Since we are calculating the gradient descent for each and every one of those parameters, the computation time is going to be obviously more than that of SGD. So yeah, if you guys would have noticed, the advantages and disadvantages of both SGD and BGD are kind of complementary, which is to say the advantage of BGD is going to be the disadvantage of SGD and vice versa. So that is why we have the third type of gradient descent, which is called the mini batch gradient descent. So yeah, as you guys would have guessed by now, mini batch gradient descent is going to be the combination of BGD and SGD. How so? So in a mini batch gradient descent, what we are going to do is that we are going to split the entire data into several different subsets. And once we are done, classifying them into several mini batches or subsets, we are going to implement a normal BGD over them, which is to say, let's say we have 1,000 parameters. We are going to split them into several subsets of 100 parameters. So finally, we are going to have 10 mini batches. So for those 10 mini batches, we are going to implement a normal BGD, which is to say, we'll calculate the gradient descent for those individual batches, and we'll take the average and we'll update the remaining parameters based on that. So by this way, we'll be able to maintain the accuracy and computation time at the same time. So that is it about mini batch gradient descent. So this will be the plot for all three of the gradient descents. So the blue colored one over here is obviously going to be batch gradient descent, as it doesn't have any random fluctuations in it, because we have taken a more representable form of data over here compared to SGD. And the purple one here is going to be SGD. And as I mentioned earlier, SGD is more prone to the introduction of noise and outliers into the data, and therefore it's going to be more of an haphazard fashion. And the third one, the mini batch gradient descent, is going to be almost similar to a SGD, but it's kind of more ordered than an SGD, because we have introduced a factor of batch gradient descent into a SGD. Therefore, it's more of a well-balanced form of gradient descent. And yeah, this table sums up whatever I've said so far. So as you can see, for BGD, we have a high accuracy and more time consumption. And for SGD, we have a low accuracy and low time consumption. Whereas for mini batch algorithm, we have both of them in a moderate and well balanced position. So yeah, now I have a question. So will the convergence be affected if in a gradient descent if the starting points differ? Just to say, let's say I'm starting from over here in the first case, and I'm going to start from over here in the second case. Will I end up at the global minima in both the cases? The obvious answer would be no, because in the second case, I'll obviously end up at the global minima. But in the first case, I'll end up in the local minima itself, because obviously I won't be able to climb back up to this, to this point, and I can't reach the global minima. So what do we do in these cases? So that's where momentum operators come in. So we'll look into that. So the momentum operator which we are going to deal with in this session is going to be SGD with momentum. So as the name suggests, it's going to be a normal SGD operator, but with an excess of a momentum term. So before going into the mathematics, I'll try to explain it pictorically over from this GIF over here. So we have two balls. Think of it as our model. So this blue ball over here is going to be that of a normal gradient descent, or SGD for that matter. And the pink one is going to be SGD along with the initial momentum, which is the one which we are dealing with right now. So as you can see, the pink ball, since it has a initial momentum, it is able to climb out itself from the local minima, which is the right one over here, and it's able to land itself on the global minima. Whereas the blue ball, which is just a normal SGD, doesn't have any momentum at all with itself. So it's going to just stay at the local minima and never attain the global minima. So that is the basic idea behind SGD with momentum operator. It tends to roll right past over the local minima and attain the global minima. So now let's dig into the mathematics behind it. It's not much, but still. So theta, theta is going to be the parameter over here. So theta t plus 1. T is going to be the number of epochs. So it means that if theta t plus 1 is going to be the parameter at t plus 1th epoch, and theta t is going to be the parameter at tth epoch. So yeah, as the formula suggests, theta t plus 1 is going to be theta t minus alpha times of vt plus 1. So if you guys can notice, it's almost the same as the parameter updation in a normal gradient descent, which we have seen earlier, except that instead of the gradient term which comes over here, we have a vt plus 1 term. So what is this vt or vt plus 1 term? So vt or vt plus 1 term can be thought of as the velocity which the model has initially. It makes sense given that we are dealing with the momentum operators. So, but yeah, so we have another formula to define vt plus 1. So vt plus 1 is going to be beta times of vt plus 1 minus beta times of the gradient. So what exactly does it mean? It means that the velocity at t plus 1th epoch is going to be the sum of a part of the velocity that has been retained from the previous epoch, which is the tth epoch, and the a part of the gradient which we have captured at the current epoch, which is this term over here. So it means that the momentum or the velocity is going to be retained from its previous epoch to every subsequent epoch. So that is going to be the basic idea over here. So, and yeah, obviously beta is going to be the factor which decides how much of the momentum from the previous epoch should be retained in the next epoch, and it's going to be called as the momentum coefficient, and the value of beta should lie between 0 and 1. So now that we have dealt with the problem of landing at the local minima rather than the global minima, what if we rolled right past over the global minima itself? Like say the pink ball has a large momentum such that it even climbs itself out of the global minima. What happens in those cases? So those cases are dealt with another operator which is RMS prop. So as I mentioned earlier, it belongs to a family of operators called as the adaptive learning rate methods. And why is the reason? First, we'll look at the parameter updation to learn it better. So as you can see, the parameter is going to be updated in a different fashion over here. So theta t plus 1 is going to be theta t minus alpha times of gt, which is almost the same as a normal gradient descent, except we have a denominator term over here in the next, the second term. So this denominator is going to be root over et plus 1 plus epsilon, where epsilon is nothing but a constant which is there to just prevent the division by zero error. So now what is this et plus 1 term? So if you can see, we have et plus 1 equals beta times of et plus 1 minus beta times of gt square, which means the square of the gradient. So the basic idea behind this is that we are going to accumulate the square of the gradients as the model progresses. We are going to record the history of the model. That's the basic idea behind it. We are going to accumulate the square of the gradients and we are going to store it under the name et plus 1. So why are we doing this? So as I mentioned earlier, we are depending upon this model, which is the RMS prop, to prevent rolling right past the global minima. So how exactly does it help us? So as you can see, the alpha is going to be constantly decreasing whenever this et plus 1 term increases, which means that as the gradient accumulates, the alpha is going to become lesser and lesser, which means whenever we are approaching the minima, after a certain point, the learning rate becomes so small that we, the steps which we are taking are going to be very precise, which enables us to even pinpoint the location of the minima. So that is the basic idea behind RMS prop. And again, beta is going to be the coefficient which decides how much of the accumulated square gradient should it retain from the previous epoch. So this is it about RMS prop. Now, there is one more point which I'd like you guys to notice. So unlike the SGD with momentum operator, we do not have a momentum operator over here. So what happens if we, even if we take all the cautions to not roll right past the global minima, what if the local minima comes first and all the caution which we have taken so far, leads us into falling right into the local minima. So that is where we have another operator which is called as the ADAM operator. So ADAM stands for adaptive momentum estimation. So here the ADAM operator is very simple. It's basically going to be a combination of RMS prop and momentum. So as you can see over here, we are going to be having two different moments over here. The first momentum is going to be mt, the second one will be vt. So this first momentum over here is going to represent the velocity momentum, and the second one is going to be the momentum that represents the accumulated square gradient, which is very similar to that of the RMS prop. So in ADAM, as it's very obvious, we are going to combine both the benefits from momentum and that of the RMS prop operators. So yeah, the parameter updation here is going to be something like this: theta t plus 1 is equals theta t minus alpha divided by this term into this momentum term over here, which is going to be a combination of parameter updation from SGD with momentum and RMS prop. So yeah, and we have an excess of a step over here, which is going to be the bias correction. So bias correction is it's going to be just the correction of bias, which is introduced by the initialization of momentum estimates to zero. Especially, it's going to be done during the early stages of training, and it has a separate formula, which is m hat t is equals mt divided by 1 minus beta 1 to the power t, and the same goes for vt as well. So yeah, we have separate coefficients for retaining the moments, which is beta 1 for the first moment and beta 2 for the second moment. So yeah, that's it about ADAM operator as well. So now we'll move on with the Slido question. Okay, so for this question, I'll be playing this video over here, and basically I want you guys to classify. Oh, sorry. So yeah, I want you guys to classify these four different curves into four different optimizers. Like you guys have to match which curve belongs to which optimizer. This is going to be the plot of optimizers against the global minima. So yeah, you guys can start the quiz. I'll give around 2 minutes for this. Yeah, before that, the four optimizers which I used over here are the RMS prop, ADAM, SGD and SGD with momentum, which basically are the operators which we have covered so far in our session. So yeah, you guys can start with that. I'll play the video now. I'll play it one last time now. Uh, Fine. I'll show the results now. Okay. So most of you guys got it right. Still, I'll give an explanation. Okay. So yeah, firstly we'll look at the blue colored curve over here. So as we know in SGD or SGD with momentum for that matter, the learning rate is going to be constant, which means the steps which we are taking along this axis is going to be constant. And yeah, obviously, as we can see, the learning rate is going to be constant only in these two cases, which is either white or blue. And it means that both red and green are going to be eliminated for SGD and SGD with momentum. Now, if we compare both the white curves and if we compare the white curve and the blue curve, we can see that the blue curve starts from the right middle of the axis, and the white curve starts from some extreme over here. It means that the white curve already has a momentum or an initial momentum which is attached to it. So that basically leads us to the conclusion that white one is going to be that of the SGD with momentum, whereas the blue one is going to be that of the normal SGD. And now when we compare these two, which is the red one and the green one, we can see the green one approaches the minima faster, and the red one takes quite a lot of time to approach it once the green one approaches it. So, and also we can say that the red one is going to take quite a bit of a detour from the minima before attaining it, which means that it has an excess of momentum which pulls it away from the minima before allowing it to land right at the global minima. So as we know that when we compare RMS prop and Adam has an excess of momentum term which is added to the RMS prop. So yeah, that's going to be obviously meaning that the green one is RMS prop and the red one is Adam. So I hope that makes it clear. Now we'll move on with the code implementation. Okay, so I hope my screen is visible. Right. Okay, we won't be doing much over here in the code implementation since the building of neural networks and all that are going to be covered in the next session. We'll just try to import all the optimizers, or at least 4 of the optimizers which we have discussed, and try to compare the accuracies between them. So yeah, the first block obviously is going to be the importing of all the necessary libraries, and after that we are going to set the seed as 42, and yeah, the next function which you guys can see over here, which is the make moons function, it enables us to create a data set on our own just by specifying the number of samples which we want and the noise as well as the random state. So this is one interesting function which you can use from sklearn to create your own data set. And after that, we're going to use the regular old function train test split to split our data into training data and testing data. So we are going to after that just standardize our data and we are going to convert it from an array to a PyTorch tensor because I hope you guys are familiar with tensors by now. So a PyTorch model is what we are a PyTorch library is what we are going to use to construct a neural network, and PyTorch prefers to deal with only tensors. So that's the reason we are converting the data type to tensor over here in this block of code. So after that, it's going to be just the construction of neural networks, which you guys will be covering, in a short while. So, and now we are going to create a function for the training of our model. And after that, we are just defining a function to plot our loss function. And now we are going to create a dictionary which consists of 4 of the different optimizers which we are going to compare, which are SGD, Minibatch, RMS Prop, and Adam. So yeah, now we are going to use this library which consists of 4 different optimizers to train our model, and we are going to obtain the outputs for 4 different optimizers respectively. And we are going to use the plot losses function which we have defined earlier to plot the loss function. And after that, we are going to use the evaluation function to evaluate the model and predict, find out the accuracy. So the final output is going to look something like this. So the green line is going to be that of SGD. It's very obvious because SGD is, as we have seen earlier, is not very accurate and it's not very effective compared to the remaining operators while we want to reduce the loss. And the yellow one is going to be mini batch. So again, we saw that mini batch is going to be doing much better than a normal SGD. And the third one, green one, as you can see, it's a bit anomalous. It's spiking up and down in the first few stages of the epochs. So why is it so? We have discussed that RMS prop completely depends upon its previous history or the accumulated square gradients to update its parameters. But in the initial stages, it doesn't have any history to look upon and update its parameters. So that's going to be the reason, for the fluctuations which are caused in this loss function over here. And yeah, after quite a bit, the loss function, the RMS prop loss function is also going to be stabilized. And the last function, which is the Adam, is going to be almost similar to RMS prop, whereas it's going to be a bit more efficient, as you can see over here, because of the momentum function which we have added to it. And yeah, these are going to be the accuracy of those individual optimizers. So yeah, the SGD has an accuracy of 84%, and the mini batch has an accuracy of 88, which is higher than that of an SGD. And RMS prop has an accuracy of 98%, and Adam has an accuracy of 99%, which is the highest of them all. So this gives us a clear idea about the comparison of accuracies and efficiency between several different optimizers, which when are going to be implemented in our model. So that is it about the code implementation part. So I'll show the attendance QR now. You guys can scan it and mark your attendance. Meanwhile, if you guys have any doubts, then unmute and ask.
A few people are confused between about the difference between mini batch and batch. So if you can explain that after that, that'll be good.
Yeah, fine. 1 second.
Wait, don't change the slide. I think it's not accepting. I'll ask them to start taking responses.
Okay. Yeah. Meanwhile, I'll try to explain it orally. So, yeah, a batch gradient descent is where we are going to take the whole data set and we are going to calculate the gradient descent for all the different parameters present in that data set. Okay, instead I'll take an example. Let's take the same example we have used earlier. Let's say we have a set of 10 parameters. So what happens in a batch gradient descent is that we're going to calculate the gradient descent for each and every one of those individual individual parameters. Which is to say, let's say the gradient descents are G1, G2, G3, so on up to G10. So in batch gradient descent, we are going to take the average of all these G1 through G10, and we are going to use that one gradient descent to update the remaining parameters. And whereas when we look at mini batch gradient descent, whenever the data is more, like let's say again we'll take the same example. Let's say we have 10,000 parameters to update. Now we are going to split it into subsets of one subset which contains 1,000 parameters. So that means we are going to again have 10 mini batches. So now that we have 10 mini batches, we can treat those individual mini batches as one parameter. Again, after that, we can just implement a normal batch gradient descent over that, which means that we are going to take a random point out of those individual 1,000 points present in that mini batch. And for that random point, we are going to calculate the gradient descent. And similarly, we are going to do that for the remaining remaining 9 batches. And once we are done with all that, we are going to take the average of that and we are going to update the remaining parameters. So that's the reason, that's the difference between mini batch and batch gradient descent. Yeah, I hope was asked the question is clear now.
Daniel, can you check meet chat? One guy has asked another question.
Yeah, 1 second. Once again, I will stop sharing for a while. So your question is, how does the loss function look like a quadratic function, right? Okay, so yeah, I think I didn't mention that because so the thing is we have used mean square error function for all the examples throughout this session. We haven't taken any other loss function, so that's the reason I've taken this quadratic looking function through the whole session. There are several other loss functions as well, and they might have a separate terrain for themselves. So I hope this answers your question. Okay, so we have another question. Only MSA is quadratic, so these optimizers will not work for. No, it doesn't mean like that. I've taken MSc just for a simple explanation, because if I have taken any other complex loss function, it won't be as simple as this to explain how the optimizer traverses the terrain to reach the global minima. So just for the simplicity, I've taken MSc. Of course, the optimizers are going to work for any loss function for that matter. Okay, the next question. Explain Atom Optimizer with comparison to RMS Pro. Okay, I think I mentioned this, but yeah, still I'll mention it again. So Atom operator is going to be the same as RMS Pro, except we're going to add a momentum operator, momentum term to that. That is going to be the only difference between Atom and RMS Pro. Yeah, so is the QR working now? Just right.
Did you change the QR?
Yeah, I changed. So yeah, that's it from my side. If you guys don't have any doubts, Arjun will take over for regularization methods.
Is the screen visible?
Yeah, it's visible.
Yeah, so if you have any doubts about the the first half, you can put it up in the group, and now I'll be continuing with the next half of the session. And I hope my voice is clear.
Yeah, it's clear. Yeah.
Yeah, cool. So hi guys, this is Arjun, and today I'll be taking a session on regularization. So I'll just give you a brief summary about what I'll be doing today. The first part I'll be covering about why we need regularization, and then what is regularization, and the different types of regularization, and the methods we use to implement regularization. So before I start off with what exactly regularization is, I'll just talk about why we need regularization. A common problem faced by most data scientists is that whenever they built a model, in any machine learning model, it used to perform very well on the training data set. The training accuracy was very high. What I mean this is, you have a model and you train it on the training data set. Before you start training, you split the original data set into training and testing. So you train it on the training data set, and then when you test it on the training data set itself, the performance is very good. It had very high accuracy. But when it was exposed to some new data set, that is the unseen test data set, uh, although it performed okay, the accuracies were not that great. The performance was not as good as the training data set. So in simple words, the training accuracy was always observed to be much higher than testing accuracy. This is a very common problem faced in machine learning and deep learning. And if you guys also try to build some model on your own and test it, you'll also observe the same problem. And so this is what we need. This is what we need to prevent or eliminate completely. That is why we need regularization. So as I had mentioned before, a universal problem in machine learning has been making an algorithm that performs equally well on training and test. So it's usually the training accuracy which is much higher than test accuracy. So we want to change that. We want to get a right balance such that both the accuracies are pretty good. And this is popularly called overfitting in machine learning. If you would have attended the earlier sessions on regression, you must be familiar with this term. If not, I'll just give a brief recap about overfitting and underfitting, and other problems related to the same. So overfitting is commonly observed when you train the data set, when you train the model for too long on the training data set. That means it learns some of the unwanted features of the training data set. The main objective of training is for the model to learn, but you should not train it for so long that it learns some of the unwanted stuff. So in a data set, this unwanted stuff is often called the noise of the data set. So you'll observe that some of the data points will follow a trend. So you can always find a nice relationship between the independent and dependent variable. But there are some points which are totally different from the trend. These are called outliers, and these outliers together constitute the noise. So what happens in overfitting is that when you train the model again and again on the training data set, it tries to fit your graph through some of the outliers as well. So these points we need to ignore actually, but that does not happen because of overfitting. It will be made more clear when I show you the graphs. I hope the graphs are visible. So in overfitting, as I had mentioned, the model is very complex. So here, this is the example of overfitting. So what happens here is the model tries to go through all the possible points. So this is the training data set as a whole. It tries to go through all the possible points. Some of these are not required because some of them are not following the trend. They are outliers. So this leads to a very high order polynomial, as you can see here, and it's a very complex model. So when this happens, the performance of the model is good for the training data set, but it makes some random predictions for anything apart from the training data set. That is not what we want. We want to generalize. We want it to perform well on all types of data. So that's why we need to reduce the complexity of the model. But we can't reduce it too much as well because it will lead to underfitting. Underfitting also is a common problem we face where the model is too simple. Like this is a straight line, it's too simple. This is not what we need. So in both of these, there are two important concepts you need to consider. That is bias and variance. Again, both of these concepts should have been taught in the regression session. So it'll just be another recap of bias and variance. So bias is the training loss basically. So it means that if your model is too simple, you get a huge loss on training on the training data set. So here the model is too simple. So suppose you predict some value at this time, the prediction will be here, but the actual value is this. So that when you sum up these errors, you get a huge error. This is called high bias, like high training loss. Training error. So that is not what we want. On the other hand, here there is high variance. what do we mean by high variance? It means it takes into account of all the points. So it's the model is very flexible for changes in training data set. Like if you add one more point and you train it again, that will pass to that point also. So it has very high variance. So we neither want high variance nor high bias. We want the best fit. We want the optimal values of bias and variance. Also, when we increase the model complexity, we have an inverse relationship between bias and variance. When we move from simple model to complex model, the bias decreases, but the variance increases. And it's the opposite when we come from here to here. So our objective here is to get the optimal value of bias and variance to prevent both underfitting and overfitting. And this concept is called bias variance trade-off. So as I had mentioned, here this is the error. This is the bias error and the variance. So if bias is too high, model is too simple. If variance is too high, model is too complex. So it's clearly visible like what I mean by complex. So we want this optimal complexity of model as well as optimal values of bias and variance. It's neither too high nor too low. So that is bias variance trade-off. It's like a trade-off. It's like you also don't become high, I also won't become high. That's what bias and variance tell each other. So you get a optimal value of bias and variance and complexity. So far I hope things are clear. This was just a recap. So these are the common problems faced by data scientists when they try to build models. That is trying to get right values of bias, variance, prevent overfitting, underfitting, and reduce the error and increase accuracy. So to prevent this, that is why to prevent this is why we need regularization. So what is regularization? Regularization is mainly to prevent overfitting. So it reduces the complexity of the model. So so what it does is that it tries to get the optimal fit and not the overfitted one. So it reduces the complexity. It reduces the order of the polynomial in the example I showed. So regularization is any modification or change in learning algorithm that helps in generalization. That means it performs well on both seen and unseen data. It generalizes. The model is very generalized. So it means you have less error and increased accuracy for both seen and unseen data. By unseen data, I mean some random data set which the model encounters. So regularization helps in improving generalization, and it prevents overfitting. And how it prevents, we will look into that in the further slides when I talk about the different types and methods of regularization. So the basic idea is it is a method, it is a change such that overfitting doesn't occur. Now we come to the types of regularization. These are not exactly the types of regularization. These are the ways in which regularization can be done. The first way is by modifying the loss function. You have the usual loss function. It can be mean square error, it can be entropy, or it can be any other type. So that is the usual loss function. So what they do here is they add some extra constraint to that loss function to get a modified loss function, and we try to minimize that modified loss function, and that also prevents overfitting. Now we have the second method, which is modifying the sampling method. So sampling method means the way we obtain our data set. So if we change if we obtain the data set in a different way, then there are chances that overfitting might not occur. And the last way is modifying the training algorithm. That we'll look into it when I go to that. It's a little different from the other two. Now we'll look at it one by one. Modifying the loss function. So this can be done in two ways. The first one is called L1 regularization, and the second one is L2 regularization. So both of them involve changing the loss function by adding some extra constraint. In the first method, L1 regularization, the original loss function is appended, like we add an extra penalty term, which is the sum of the absolute values of weights, which is summation WI here. So this loss original can be any loss function. We usually take the mean square error and we add the sum of the absolute values of weights. What are weights here? Like even in linear regression, you would have learned that we try to find a relationship between the independent and dependent variable. We write y as wx plus b. That is simple linear regression with one feature. Suppose you have many features. Suppose you want to uh, predict the price of some site, price of some a house. That will have many features. You look at number of rooms and the location, etc., etc. They are the different features, and they each of them will have one coefficient. That is the weight. So you can establish a relationship between y, that is the output, and the different x's, that is x1, x2, x3, using this. So we can write y as w1 x1 plus w2 x2 and so on till how many other features you have, plus b, which is the bias. So this is linear regression with multiple features, and those are the weights I've mentioned here. So what this does is, our main goal is to reduce this loss function, this the new loss function. Originally we were using only this part, so our only objective was to reduce that mean square error. But now we also have the weights. So suppose your mean square error is low, but your weight values are very high, you will still have a high loss, a high overall loss, that is the L1 loss. But we don't want that. So what is the objective here? It not only reduces this original loss, it also tries to reduce the values of these weights, the magnitude. Suppose you have a function y equal to 3 plus 2x plus x square plus x cube. So the 3, 2, 1 and 1 are the weights. So it tries to reduce the weights, and finally you get the optimal value of weights such that the loss is minimized. So if you want to obtain the lowest loss, then the best method is to make these weights zero. Not all of them, at least a few of them. So basically, when we do that, when we make a weight zero, it means the corresponding feature, we are ignoring that feature. Suppose you have three features. So you write the relationship as w1 x1 plus w2 x2 plus w3 x3. So if you make w3 zero, we are completely ignoring the feature x3. So in a way, L1 regularization performs feature selection. Feature selection, it's very clear, right? It's selecting features, but we don't do that. The model itself does it, such that the loss is minimized. So not only does it reduce the loss, it also helps in feature selection. So suppose you have thousands of features, some of them you don't want. You don't know which one to ignore. This does that automatically. Also, there is one term, lambda. There is one constant which I have not mentioned, which I have not told what that is. That is a hyperparameter. I'm hoping you guys know what a hyperparameter is and how it's different from normal parameters. Hyperparameter means the model doesn't learn that. It doesn't update values. We give the values. We can give it any value. So if we can tinker with it, we can modify the values such that we get the best accuracy. So here lambda, we can increase or decrease the value of lambda, which also increases or decreases the effect of this regularization. This is also called lasso regression, by the way, L1 regularization. So how does it increase or decrease the effect? Suppose you increase the value of lambda, it means this, suppose you make this 100 or 1000, then this overall loss value will become high. So then what happens is, to make that low, these weights become very low. So if you make this high, this should become very low. By making them low, it means you are performing, we are increasing the effect of regularization. So, but in the, instead of that, if we decrease the value to say 0.5, then this can have some nice non-zero values, and we can still obtain a low loss. So lambda can be increased or decreased to, increase or decrease the effect of regularization or lasso regression. I hope this is clear. I'll be moving on to the effect on the model. All of this I've already explained. So it's just a recap again. So L1 regularization or lasso regression has a tendency to drive some model coefficients to zero, meaning we are ignoring some features because we want the loss to be low. So this is beneficial when we deal with high dimensional data. So high dimensional data has many features, too many features, and too many things we need to look at while learning. So we don't want that. So some of these features are ignored, and that is done through L1 regularization. And we don't have to do that. The model itself performs that. So it simplifies the model. So again, initially I had mentioned that to reduce of overfitting, we need to simplify the model. We might reduce the features, we might reduce the order of the polynomial. That is done through L1 regularization, and again it helps overfitting, and our objectives accomplished. This is one type of regularization that using changes in loss function. The second type is called L2 regularization. It's also called ridge regression. You can see it's very similar to the earlier one. Original loss plus lambda times some extra constraint. Here is just the absolute values. Here is the square of the absolute value. You might say like, how is it different? It's almost the same. Finally, you make the weights lower. But the thing is here, although the weights tend become like lower, the values, it doesn't become zero completely. Why? I will explain. So here these weights, as they go below 1, when they go to say 0.4, 0.3, since the loss has the weight squared, when you square some numbers below 1, 0.3 squared becomes 0.09. So it's a very small number already. So there is no requirement to reduce it further. So the difference between L1 and L2 is that here it has tendency to drive these weights to zero completely. Here it need not become zero, but it still reduces its magnitude, thereby decreasing the model complexity and the loss. So as I mentioned already, the main effect is to shrink the coefficients to zero. But unlike L1, it does not sum to zero completely. And how L2 regularization helps is that although it doesn't perform feature selection like L1, like it doesn't eliminate features, it still reduces the effect of some features, and thereby some maintaining a balance between the features. It does not like no feature has a big upper hand. Say no feature becomes dominant. Every feature is has some say in the model, and the complexity decreases. So it maintains a balance. It doesn't become overly reliant on any one feature. So by doing this, the model complexity is also reduced, and it prevents overfitting. So now you might wonder why are we making weights like lower and how does it reduce model complexity? So I give you a simple task or a homework. Just go open Desmos. I'm sure you guys will know what Desmos is, and try plotting a fourth order polynomial. Say 5 plus 3x plus 2x square plus x cube plus x power 4. And then after you do that, slowly start reducing the values of coefficients of higher order terms like x power 4 term, x power 3 term, x power 2 term. When you reduce the coefficient, you will see that the curve becomes like a little more flatter. It will slowly start approaching a straight line. So when you reduce the coefficient values, I'll just go back to this slide. When you reduce the coefficient values, you move from this to this, from a very higher order polynomial to an almost lower order polynomial. It's not a lower order polynomial. It looks like that because the weights have become lower. So this is what we want, and that is done through regularization. And I'm sorry I went back. So that is the difference between L1 and L2. To recap, L1 makes some weight zero completely, but L2 reduces the value but doesn't make it zero completely. So moving on, now I'll introduce something called sparsity. Sparsity, you can pronounce it in whatever way you want. So as I had mentioned, the difference between L1 and L2 lies in feature selection. So here sparsity refers to the number of feature coefficients that are reduced to zero. In L1, because of that absolute value penalty term, it makes some of the weight zero completely, but in L2 it doesn't make it zero completely. So L1 L1 promotes feature selection, while L2 reduces complexity. Both of them lead to reduction in overfitting in their own different ways. Both of them are very powerful, but they are little different in the way they perform reduction in complexity. So you can just go to the slide here. It's exactly what I mentioned earlier. Feature selection, making some of the coefficients zero. And in L2, it doesn't perform feature selection. So it doesn't make the value zero completely, but make it lower. So that is the difference. And the number of coefficients reduced to zero are called sparsity. So there's high sparsity in L1 and low sparsity in L2. This is the main difference between L1 and L2. So before we move on to the next type of regularization, I'm hoping all of you are clear with what I've explained so far. So you'll have to answer this simple Slido question. I'm hoping you're able to scan the QR. If you're able to scan the QR and answer the questions, please let me know. Yeah, the poll is active now. You can start giving your results, your answers. Can we make lambda value negative to reduce loss? That's a good question. You are trying to reduce loss. So that is not the main goal here. You can just put some minus 1000 and make loss zero. Suppose you get original loss is 1000. You put minus 1000 and make it zero. That is not the goal. We give positive values to lambda such that the weights are also made lower. It's lambda multiplied by the weight summation. So our objective is not just to reduce loss function, it's also to perform regularization. The point of regularization is lost if you make lambda negative. I see only 52 have answered. I hope you guys are able to scan it and answer the question. The increase, regardless of the increase, from where to where you increase, you still have the same trend. The effect might be a little lower, but the trend is same. So don't get confused. I don't see any increase in number of people answering, so I'll just share the results. So yeah, that's correct. If you increase the value of hyperparameter lambda, the effect increases. So yeah, it's pretty simple. It's exactly what I explained in the slides. Uh, if we increase a parameter lambda, hyperparameter, the weights would want to become zero. So it increases the effect. That's it. It's pretty simple. So I'll stop this now. But there must be a limit to the extent which we can increase lambda. I have not heard about any upper limit as such. You can, as I said, it's a hyper parameter. You can play around with it. It has no limits. You can make it 1 million if you want to, ignore all features. But it's yeah, correct. You're right. If you make it extremely high, the model might become too simple. But that is why it's a hyper parameter. It allows it's like we have the power to change it based on our requirements. If we want to get a a good accuracy, we can increase it up till one extent such that the accuracy is high. Suppose you increase it beyond say 1500 and you observe that your accuracy is decreasing, then you stop. That's where you stop. So you play around with the values. Yeah, I hope the screen is visible. But Daniel, is it visible? Is the screen visible? Yeah. Uh, you asked if it doesn't it make option B correct? No, the effect of regularization still increases. If the effect is useful to us or not, that is different, but the effect still increases. So yeah, I'll be moving on to the next part. So now that I've taught modifying the loss function, now we'll be looking at modifying the sampling method. So overfitting can also occur if you have a very small data set. Like if your data set size is very small, suppose you're performing some regression tasks on some flower data set or whatever you want, and then you only have like 3-4 flower samples, then you don't have a huge data set to work with. That time you're okay, to make it simpler, suppose you have only 3 points in your graph and you try to fit a curve. You'll try to go through all the 3 points, and suppose you get a fourth point, it may not predict it properly. So when you have a small data set size, it often leads to overfitting. So modifying sampling method is getting the best out of our limited data. So the way we use our data to decrease overfitting and get our best accuracy. So the first method is called data augmentation. So in data augmentation, it is usually used in image classification and CNNs. You will learn CNNs later. They're called convolutional neural networks. So whenever you deal with images, suppose you have one picture of an apple, so that's not enough. So to generate more, what we do is we artificially make generate more, increase the data set size by making some changes. So this includes cropping, dilating, rotating, adding noise, decoloration, and then making it increasing brightness, reducing brightness, and rotating, getting mirror image. There can be so many things you can do with one image to get more images. So that is called data augmentation. So that helps increase the data set size, and it helps in improving our model's accuracy and reducing the complexity. So thereby it prevents overfitting again. So the same our objective is achieved. So this is is a good pictorial representation of how data augmentation works. So you can, deep, intricate details are lost, decolorize, edge enhanced. So all these edges are more darker. Then salient map, flip, rotate, crop. So many ways. So this can you can generate like hundreds of images out of one image. So that will help improve your model's performance. That is one way of modifying the sampling method. The other method is k-fold cross validation. This is a very interesting method because it doesn't make new, it doesn't generate new data. We play around with our data itself such that it appears that we have more data than what we already have. So what we do is we have a data set given. It's a reasonably small data set, not too large. We split the data set into k subparts. K is again a hyperparameter. You can choose a value for k. So you can split it into 5, 10. 10 is usually what we do. We split it into say 10 parts, k parts. So we split it into k parts, and only one of these k parts we use it for testing or validation, and the remaining k minus 1 parts we use it for training. So we split it into k parts. We use the first part, remaining as training. Now we use the second part, and again remaining as training, and so on till we use all the k parts. So what we do is every time we are training, we are not training on the same data set. This train and this train are not same. But originally we had only one data set. We are trying to extract maximum information out of that data set by splitting it into k parts and using k minus 1 for training, and the remaining for testing. So this is very useful if you have a limited data set size, and if it's very small. So if you want to get a better performance out of your model through small amount of data, you split it into how many parts you want. Take one part as test or validation and train it on the remaining. So by the looks of it, it'll look like for the model, this will look like you're giving it different types of different data. Like what do I say? For the model, all these 5 will not look the same, although the entire data set is same. So that's the main objective. We are artificially increasing our data set size, and again preventing overfitting and increasing, enhancing the performance. So this is the algorithm in which it's performed. You shuffle the data set. So you'll have some order in which you collect it. Collect the data, you arrange it in some order. You shuffle it first, then split it into k parts. Keep one fold for testing, remaining for training, and then again do the same thing for all the parts. Repeat the process. So finally, we get you get the accuracy scores. Usually, as and when you keep training it for different parts, your accuracy slowly starts increasing. And finally, what we do, we take the mean of all the accuracies, all the scores, and that is our actual model's performance. Initially, the first time you train it and test it, you might get a low performance, low accuracy. And then finally, when you do it for all the k folds, the accuracy keeps increasing. We will not take the maximum one, of course, that will be false. So we'll take the mean, we'll take the average of all the accuracies. So that is k-fold cross validation. It's again very simple. It's just a nice way to increase our data set size. Yeah. So next, this is the last method, which is modifying the training algorithm. Here, there are things you might not understand right now because you haven't you haven't gone into depth in when it comes to neural networks. You will understand this much better in the next session on PyTorch and neural networks. As of now, just try to, I will give you a high level explanation. You'll get a high level understanding, not too much in depth. So I've covered only one main method of modifying training algorithm, that is dropout. So this is called dropout regularization. As Daniel had mentioned, this neural network usually looks like this. It's modeled on our neurons in the brain. So you have an input layer consisting of 2 neurons here, and a hidden layer consisting of 4 neurons, and an output layer. Basically, these are the input features we give, and these are the outputs we obtain. That is what we need. That's the target. So we perform some calculation here. We multiply it with weights. We add bias. Every time we move from here to here, every every thread connecting here to here is performing some operation on your data. And then after all these operations, after passing through many functions, the output will be the output you want. Initially, you will not get that. You have to train it, and then you'll get the required output. So this is how a neural network works. Basically, you'll get a clearer understanding in the next session. So in dropout regularization, we have a hyperparameter called dropout ratio P. Okay, so what dropout ratio does is it's a value between 0 and 1, which describes which basically tells what percentage of the total connections are dropped. So these are the connections here. So when we say dropping a connection, you can see that this connection fades off, meaning we are dropping this connection. This operation we are not performing. So that's as good as dropping this node. So suppose you have say 4 nodes here, and you give dropout ratio P equal to 0.25, which is 1/4. So every time you train, every epoch, there's a probability that there's a 1/4 chance that each one of them are dropped. That means in simpler if I explain it in simpler words, every time at least one of these 4 is dropped. It can be at some epochs none of them can be dropped, and some epochs 2 of them can be dropped. On average, one of these 4 are dropped if you use probability as 0.25, that is 1/4. Here I've given 0.3, but I used 0.25 as the explanation, as the example to explain. So don't think too much about this. Basically, you have a bunch of connections in this neural network. You give some value P, and based on what fraction it is, that fraction of the nodes are dropped every time you train. And what this does is that every time you train, different nodes are activated, different nodes are dropped. So it trains in a different way each epoch. So this somehow increases the accuracy. Why? What is the math behind it? You will learn later. But this is how it works. This is one method introduced by data scientists, that if you drop a few nodes in your neural network, it somehow managed to increase the accuracy. This is called dropout regularization. So what this does is it makes the model more robust, and it tries to get maximum output out of the limited data we have. So the dropout ratio is a hyperparameter. The value P I mentioned here is a hyperparameter. It's between 0 and 1. So usually 0.25 to 0.4 is what we take to while performing regularization. You can take other values as well, but this is the optimal range. So just a recap, you have a bunch of nodes, you give a value P, and based on that value P, the fraction P of the total nodes are dropped, and somehow it reduces the overfitting, increases accuracy. That's the last method, that is modifying training algorithm. So that's it when it comes to regularization. So the summary is that they're basically different changes you do perform in your training algorithm. That is, you can change the loss function, or you can change the algorithm, or you can change the increase the data set size artificially. By this, this increases the accuracy and decreases overfitting. Now I'll move to the next part, which is code implementation. Before I move to code implementation, you have to answer this simple Slido quiz again. It's based on data augmentation. I hope you guys are able to start answering. This is a very good question. If you can play around with the values, doesn't it mean that we can use an optimizer to uh, optimize it, the hyperparameter? If we cannot do that for hyperparameters, because we basically have to iterate through all possible values. There is no sense of direction as to where you have decrease in loss. So that, we usually try to provide many values, try it out, and then you can get a better accuracy. So we usually never perform optimization for hyperparameters. It's usually trial and error with multiple values. And many scientists have already done the trial and error, so they already have an optimal range. So every value in that range does equally good. So we usually perform trial and error and get our own optimal value of hyperparameter. It's a very simple question. I hope all of you attempted. Yeah, I don't see any new participants answering, so I'll share the results. Yeah, it's a very straightforward question. It reduces accuracy. It helps in reduction of overfitting, increases size of data set, and also helps in diversifying the data set. Yeah. So I'll stop this. I hope the slide is visible. Sorry, I'll move to the code implementation now. It's a very simple code implementation. We'll just be working on a housing price data set. I'll show it. Is the screen visible? The code. I'm assuming it's visible. So yeah, so we'll be finding how finding out how regularization improves the accuracy and how it reduces overfitting. So we'll be using the Melbourne housing price dataset. First, we need to import the necessary libraries, NumPys and pandas to deal with our CSV file. So dataset equal to pd.read CSV. We read our CSV file, which is the Melbourne housing price dataset. I've already shared the dataset, so you can go through it. Dataset.head prints the first 5 rows. So this is a very large dataset. It has multiple features: suburb, address, number of rooms, and the seller, the postcode, number of bathrooms, etc., etc., etc. There are many features. So that calls for regularization, right? Because it's feature selection and reducing complexity. So that is why this is a good example to show why regularization works. So our objective is to predict the housing price given the features. Now this is not, we cannot directly work with this. We have to perform some pre-processing. You would have learned about data pre-processing. There are many methods. this data set consists of many, nan values. These are empty values that doesn't have any value. So we have to remove those or fill it with something. And it also has text. We have to convert this to numbers. Only then we can train our model. So we first print the number of unique values in every column. So suburb column has so many unique values, and address, rooms, and so on. Now we perform feature selection manually before regularization. We just choose some of these features, some of the important features. Then these are this list contains the columns we are using. Suburb, rooms. We are almost using all of them. A few of them we are neglecting. So like longitude, latitude is something not required, right? Why would you care about longitude, latitude in Melbourne housing price data set? It won't make sense. So we're ignoring such columns. So these are the columns we choose, and then we again we modify the data set, choosing only the required columns, and then again print it out. These are the selected features. This is the very first step in pre-processing. Now you find out how many entries are missing in our data set per column. So there's a nice pandas function called df.isna.sum. It provides the sum of the missing entries. So bedroom, bathroom, car has so many missing entries, and the region name. These are text entries, so we can't even fill them. So region name and what else? Building area, etc., etc. So first step is to fill some of these, and next is to drop some of these. So we choose to fill bedroom, bathroom, and car with zeros, like just zero. We can see that there are some values with car 0. So we fill these with 0. So after you fill that, we use dataset dot fill na, and we can fill it with whatever number you want. This again, you can fill it with whatever you want. Which again, we experiment with it, and then whichever performs better, you choose that. After that, we again print the remaining null values. We still have quite a few. And what we do is, in land size, building area, and all, we fill it with the mean. We fill the data set, the missing values with the mean of the remaining values. That is done using dataset.fillNA, dataset.landsize.mean. So there are many functions provided by NumPy and Pandas. Right now, many of them might be new. As and when you perform more and more, as and when you build more models and you work with data, you'll get used to some of these. You don't have to memorize it. You can always refer to Pandas and NumPy documentation. So we fill land size, building area, distance with the mean. We cannot fill property count with mean because property count is an integer. We cannot. Sometimes you can have, this mean can lead to fractional values. We won't want that. It won't make sense as well. So we fill that with median. And again, we print the missing values of the remaining missing values of the changed data set. You only have like region name and council area with 3 missing entries. They are names. You cannot fill it with any value. So what we do is we drop those 3 rows, whichever has nan values. Finally, you only have these many. So finally, you only have the data set without any missing values. So this is the changed data set. So data set that drop any will drop all the rows with missing values. So we have done with the beginning of data preprocessing. The next part is to convert text into numbers. You have names, so many names and areas. So we use something called pd.getDummies, Pandas getDummies function. It encodes these text values, encodes text based on some algorithm, and it converts them into numbers. So this is a very useful way of encoding. There are other methods of encoding such as one-hot encoding, etc., etc. You can go through encoding later just to explore and learn better. But here I've used pd.getDummies. So finally, you have our pre-processed data set. Now we are ready to work with our data set. You have no missing values, and all the text entries are converted to numerical values. So now we perform linear regression, and then we perform regularization on our model to see if the results are better. Here we'll not be doing anything from scratch. Everything is done by importing from sklearn. So it's very simple. It's extremely simple. In fact, just a few lines of code. So we split the data set into features and target. So we main goal is to predict the price. So we choose the price as target. Remaining all columns are features. So drop dataset dot drop axis equal to 1 means along the columns are dropped, not the rows. So only price is dropped, everything else is considered as feature. Now we use sklearn.model selection. We import train test split, again splitting the features into training and testing, the data set into train and test. And as I had mentioned in the last lecture as well, make sure that you give the same order of X train, X test, etc. I've given 0.3 as the test size, meaning 30% of the data set is test data set, 70% is train data set. This random state is how that again is a hyperparameter. You can give any number you want. It different numbers will give different random fractions of our data set as test. That's all. So now that we split the data set into train and test, we perform linear regression on this data set. So by linear regression, what we are doing is suppose we have 15 features and we want to predict the price y. So the y the price y can be represented as w1 x1 plus w2 x2 till w15 x15, because there are 15 features, plus b, which is the bias. That is why we are using linear regression. We are establishing a linear relationship between the independent and dependent variables. So we then fit the model. That is, we perform linear regression. We just have to do dot fit. It's very simple in using sklearn, and we use reg.score to predict print the accuracy. So when you see the accuracy on our test data set is very low. It's 13%, 0.13 with linear regression. But on the training data set is very high. That means that is what I had mentioned earlier. It's overfitting. So what is happening here is that the accuracy is very high for train and very low for test. That is the main problem we encountered initially. So we have to see if regularization performs better. Now we import a linear model from sklearn, and we use the lasso regression here in the first method, that is L1 regularization. So we use L1, and then again after that we again find the accuracy. For test it is 66%. Again here, as I mentioned, you just have to do dot fit. It's very simple, and then print the accuracy. We got an increase from 13% to 66% on our test data. So that is a very huge increase because of lasso regression or L1 regularization. Some of the features are removed. We don't want them, and we get a better model with lower complexity and increased accuracy. And the test train accuracy is still pretty high, 67. We can perform the same thing, but with ridge regression, that is L2 regularization. Again, the ridge regression, dot fit, X train, Y train, and print the score for test and train. We get 66% and 66%. Again, it's an increase. Test score is 66. It was 13 initially. This alpha value is the hyperparameter lambda, what I had shown. We have the loss plus lambda times the sum. That a lambda here is alpha. You can give whatever value you want. You can play around, and the number of iteration it performs. So that's pretty much it. You can see that there's an improvement in accuracy on our test data set, and that is our objective, and we have achieved it through regularization. So I hope things are clear. If you have any doubts, you can put it in the chat, and you can go through this code implementation again. If you have any doubts, you can message on WhatsApp as well. Now I'll be moving to I'll be sharing the attendance QR now. Yeah, I hope the QR is visible. Toll is the tolerance value, that is up to how much how much error can be tolerated. Okay, we'll ask them to open the attendance form. 1 second. L2 is giving more accuracy, L1 or L2 always better. So it's nothing like that. In our particular data set, it's observed that L2 is L1 is giving better, but again depends on data. 66 is a low score. You are right. We are using linear regression. We are not using some complex model. Linear regression is a very simple model, so obviously you'll get a low score. But the point I'm trying to make is when you perform regression, when you perform regularization, there is an improvement in accuracy when you when you test it on the test data set. And yes, the session is over. So if you're, are you guys able to scan the QR and fill attendance? Yeah, so please fill the attendance fast, and once you're done, unless you have any doubts, like if you have doubts, you can stay. If not, you can leave. Just to clarify, dropout regularization, I think, was a little bit tricky because you wouldn't have, come across neural networks. In the next session, you'll have an introduction to PyTorch and neural networks. After that, it will be very good if you go through these slides again. You'll understand it much better.